Hey everyone, so today we are talking about salts and KSP. They are related in some way. So when we have an acid-base reaction, it usually always produces water and it produces a salt. And those salts, depending on what their makeup is, they could be acidic, basic, or neutral. So we'll talk about that today on how to identify as those salts, acidic, basic, or neutral. And later we'll talk about KSP, which is kind of like the dissolution of those salts, or the dissociation of those salts, and how we get a whole range of different calculations we can do for those salts. It's a lot like equilibrium, but it is tricky at some point. So please make sure that you are paying attention, you have good attention to detail, because sometimes you could get goofed up on these types of questions. But first, let's take care of the easy thing. So like I said before, salts can be acidic, basic, or neutral. So on the AP exam, they'll give you something like a salt, such as iron 3 nitrate, and they will ask you, is this salt acidic, basic, or neutral? And the way we figure that out is that we just split the salt apart, and then we add H plus to the negative ion and OH minus to the positive ion. And you'll see what I mean here in a second. So this iron nitrate ion will break up into iron 3 plus because there was 3 negative 1 nitrates with it, and it'll break up into nitrates. And what we do is we go ahead and add OH to the positive ion and H plus to the negative ion. This shows us what their original basic form or acidic form were. So what we'll do is we'll add OH to this positive ion, making it OH3. And we'll add H plus to this negative ion, making it HNO3. And then what we do is we look at these and we determine if they are a strong or weak base or acid. So I'm looking at FeOH3, and I know this is not one of our strong bases, so it is a weak base. I look at this acid right here, nitric acid, that is a very strong acid. So this is one of our strong acids. So I look at these and I say, which one overpowers the other? Is the strong acid going to overpower the weak base? Yes. So this means that this salt was acidic, right? Again, we're taking our salts, we're splitting them up, we're seeing what they derive from, either a strong acid or a weak acid, or a strong base or a weak base, and we see which one is stronger. And that will determine if our salt is acidic, basic, or neutral. Let's do another one to go through this, just to make sure we're getting it down, okay? Let's say we have sodium ethanoate. Okay, so this was the salt that was formed between an acid-base reaction. First thing we're going to do is we're going to break it up into its ions. Sodium is going to be one of them, right, Na? And then this guy is ethanoate, which is C2H3O2 minus. We add an OH minus to our positive ion. We add an H plus ion to our negative ion. Now we identify these as strong acid, strong base, weak acid, weak base. NaOH, that's a strong base. HC2H3O2 is a weak acid. So the base overpowers the acid, so this was a basic salt, a basic salt. Alrighty, let's do another one. Let's do KCl. KCl, that's a salt. Is it acidic, basic, or neutral? Well, let's find out. We split it up into its ions of K plus and Cl minus, right? We add OH to the positive ion. We add H plus to the negative ion. And then we ask ourselves, are these strong acids or strong bases? You should have these memorized, right? If you don't, better get to it. Strong base, strong acid, they cancel each other out. So this, in fact, is neutral. Okay? So again, we're splitting it apart. We're giving them OH and H plus. We're determining which one's stronger. Based on that is if our salt is acidic, basic, or neutral. Okay? There is a situation where you could have a weak acid and a weak base, and I'll show you an example of that right now. Say we just had something like NH4NO2, okay? So this would break up into NH4 plus NO2 minus, and this would be nitrous acid, which is weak, and this would actually be NH3, which you could add OH to it. Let's just keep it consistent. Okay, so this is a weak base, and this is a weak acid. And what you could do is they would have to give you the Kas and the Kbs for these, and whichever one is larger is going to be the one that determines if it's strong or acidic or basic. So let's just say that the Ka for this one was 1 times 10 to the negative third, and this one was 1 times 10 to the negative second. This one is greater, Ka, which means it dissociates more, so that means this would be acidic. I have never seen ones like this on the AP exam, but who knows what they could throw at you, okay? But either way, it should just be simply breaking it up, making them into acid bases, and seeing which one is stronger to figure out if our salts are acidic, basic, or neutral. So that is it for salts. Let's go on to the more mathematical topic, which is KSP. All right, everybody. So again, we're talking about KSP and molar solubility. Molar solubility is just chemistry slang term for concentration of a salt ion. So anyway, what is KSP? So we've been talking about things like Kc, we've been talking about Kp, concentration, pressure, right? We've talked about Ka, which is acid, we've talked about Kb, which is base. Well, KSP is just the same thing, but it just deals with salts. Really, really insoluble salts, okay? So usually your KSPs are really, really small numbers. We're talking like 1 times 10 to the negative 20th. We're talking 1 times 10 to the negative 32. We're talking really, really, really small KSPs. So it is a very similar type of problem like with our equilibrium section and our weak acids and weak base section. But again, it just is a little bit more difficult because you got to pay a little bit better attention to detail. So first, let's talk about the dissolution or the dissociation of these salts. So what you'll have is you'll usually have a salt, and our first example is something like KaF2. Okay, we want to show the dissociation equation for this. So what will happen when it'll go in water? Well, these KSP salts are always going to be solid on the left side. They're never going to affect our equilibrium later on, and you'll see that, okay? And what we'll have is these double arrows, right? And then this will dissociate into its ions. Well, these things can totally dissociate. It's not like acids where it only donates 1 proton. This thing will fully dissociate into its separate ions. So it will dissociate into Ca2 plus Aq and 2 F minuses Aq. All right, so we had 2 fluorines there, so now it's going to dissociate completely into those 2 F minuses. So be aware of that. When you have been in the trend of acids and bases where you're just giving up 1 H, well now with KSP, whenever you see a solid on the left side, we're dissociating it completely into its ions. So what would the KSP for this be, right? Our KSP expression, remember, it's products over reactants. Well, remember, our reactant is a solid, so it is not going to be included in the KSP expression. Okay, that's going to be for all of these. You're only going to have one line the whole time. There's never going to be a products over reactants because the reactants are never included in this. So it's just going to be, we're going to have concentration of Ca2 plus for one of them, and we're going to have concentration of F minus for the other. But am I missing something? Yeah, F minus has a 2 in front of it, so you better square it. This is the biggest thing that people goof up. They forget the square, or they forget the 3, or they forget the coefficient and forget to put it in their equilibrium expression. Make sure that you do that, okay? Easy goof up that people make all the time. Let's do another one. Let's do, what else do I got written down here? Let's do another dissociation equation for a salt. We got silver to chromate. It's a solid. Okay, they're always going to be solid on this left side. Now, it's going to dissociate. Well, it's going to dissociate into its ions. So it's going to dissociate into Ag+. But remember, I got 2 of them. And this guy should be familiar. It is our chromate. It's going to dissociate into CrO4 minus AQ. We're going to go ahead and we're going to write our dissociation our KSP equation for this. Ag plus CrO4 minus. Don't forget that squared because there's a 2 right there. Okay. And let's do one more. Just for the fun of it, let's do it again with our pal silver. But instead of silver chromate, it's silver chloride. Again, these KSPs are always going to be solid at the start. And this will just dissociate into Ag plus and Cl minus. No plus sign in there. I don't know why I put plus in there. And then our KSP. Remember, this guy doesn't affect it at all because he's a solid. It's going to be Ag plus and Cl minus. So that's just a good thing to learn. Always write these KSP expressions, okay? Because you guys will sometimes forget the squareds that are incorporated in here, and it's always just good to write those down anyway. So let's go ahead and let's talk about this molar solubility thing and doing some problems here where we're gonna have to use ice tables. So here is our first example. Calculate KSP of PbCl2 in water if the molar solubility of Cl minus is 1.62 times 10 to the negative 2. Like I said, molar solubility is just kind of a different slang term for concentration. So when I say molar solubility of Cl minus, that means concentration of Cl minus after it dissociates. So technically at equilibrium. Alright, so when you see that molar solubility, don't freak out. That just means concentration of Cl minus. So here what I want to do is I want to figure out KSP. Well, remember KSP is product over reactants, but we don't have reactants. So anytime we got to figure out like Ka, Keq, Kb, we got to have an ice table. So let's go ahead and do that. So let's figure out the dissociation for this solubility salt. Remember, it's PbCl2, so it's going to dissociate into Pb2 plus Aq and 2Cl minus Aq. Right? We're going to dissociate into those 2 chlorine ions. Ice table time. Remember, solids don't matter in terms of ice tables or equilibrium, so just forget about it. We don't care about him. All he tells us is what our ions are going to be. Okay. Equilibrium, nothing. Or, sorry, initial, nothing, right? We haven't dissolved it yet. We haven't put it in water. This guy is plus x, and now we're getting back to something that we haven't talked about since equilibrium, right? This is going to be plus 2x because there's a 2 in front here, right? And now, molar solubility. Remember, we don't have any equilibrium concentrations unless they tell us. Remember that molar solubility is just the equilibrium concentration. So, in this case, it is 1.62 times 10 to the negative second. And this guy will be x. So we have to figure out x, and then we could plug it into our KSP expression, which is going to be KSP equals Pb2 plus. Don't forget Cl minus squared. So we got Cl minus, that's cool, but now we need Pb2 plus. Well, remember, initial plus concentration equals equilibrium, so right now we pretty much have 0 plus 2x equals 1.62 times 10 to the negative 2. So let's solve for x. 1.62, second e to the negative 2 divided by 2. So our x is going to equal 0.0081. So now we have x, so that means we have our equilibrium concentration right here. So now it's just a matter of plugging and chugging into our original KSP expression. So I'm going to do that right now. So we want KSP. Our lead equilibrium concentration was 0.0081. Our chlorine concentration was 1.62 times 10 to the negative second. Remember, that is to the squared. Okay, so let's go ahead and let's plug this in. Times 1.62 second e to the negative 2 to the second. And I got a KSP of 2.12 times 10 to the negative 6. I want to just double check this one last time. Yes, that is correct. So that is our KSP. So remember, molar solubility just stands for that equilibrium concentration of whatever ion we're talking about. So make sure you understand that. Make sure you understand your ice tables. Make sure you're remembering for change to include the coefficient of that 2 in front of that Cl. And remember to include it in your KSP expression as well. Let's do another example like this. All right, everyone. So here's another example. So here it says calculate KSP for Bi2S3 bismuth sulfide if the molar solubility is 1.3 times 10 to the negative fifth. Here, they don't give you an exact specific ion in which this molar solubility is referring to. They just say if the molar solubility is 1.3 times 10 to the negative fifth. In that case, you could just assume that X is going to equal 1.3 times 10 to the negative fifth. Sometimes they're vague like that, okay? When they say molar solubility, just assume that means X, okay? If they don't specify, molar solubility is just X, all right? So what does that mean? Well, let's go ahead and let's set up our equilibrium expression. Let's set up an ice table, and let's see if we can figure out KSP. So here we got bismuth sulfide, right? It is a solid, and it's going to dissociate into bismuth 3 plus, 2 of them, and into 3 sulfides. Right, let's go ahead and let's do our ice table, and we'll do our KSP expression later. Initial concentration, right? We never have that on the solid side. It doesn't matter because it doesn't affect equilibrium. These are always 0. Here we have plus 2x plus 3x. And for now, let's just put 2x here and 3x here. Remember, if they don't give you any specific molar solubility, you could just assume that the molar solubility they give you is 1.3 times 10 to the negative fifth is X. So what we can do is we could plug X in for both of those to get the equilibrium concentration. Okay, they will do that sometimes. So molar solubility can be very vague. It could just mean X. Sometimes they'll give you the molar solubility of Bi3+. That'll be the whole equilibrium concentration. I know that's confusing, but that's what they'll do sometimes. Okay, so molar solubility is X. Let's go ahead and plug it in here and get our equilibrium concentrations. So we'll take 2 times 1.3 second e to the negative fifth is 2.6 times 10 to the negative fifth. And then I got, once again, 1.3 second e to the negative fifth times 3, which will be 3.9 times 10 to the negative fifth. So now we have both our equilibrium concentrations, right? Now KSP, can't just multiply those together, right? We got to figure out if any of these are to a certain exponent, which they will be. KSP equals bismuth 3 plus to the second and sulfur 2 minus to the third, right? Because those coefficients are in front of them. So now let's go ahead and let's plug in our equilibrium concentrations. We got KSP equals 2.6 times 10 to the negative fifth to the second, and then 3.9 times 10 to the negative fifth to the third. The big mistake people make is they forget to add the 2 and the 3 there. I know it's redundant. I know that we've been dealing with that for a while now, but that's just how it goes. It's redundant, okay? So 2.6 second e to the negative fifth to the second times, this is going to be real small, 3.9 second e to the negative fifth to the third. I got 4 times 10 to the negative 23rd. 4 times 10 to the negative 23rd for our KSP. That is a really, really small KSP. But That's how it goes, okay? So, again, molar solubility can mean X if they don't state otherwise. Molar solubility could be the equilibrium concentration like in our last example where it said molar solubility of Cl minus. All right, let's do another example where they ask for us to solve molar solubility. All right, so here it says calculate the molar solubility of AgCl when Ksp equals 1.8 times 10 to the negative 10th. Here, when they're saying calculate the molar solubility, what you are going to be solving for. Remember that molar solubility, if they're vague, equals X. So what we're going to be doing is solving for X, our change pretty much. So the first thing I like to do is just write the equilibrium expression and see where it takes me, okay? AgClS, Ag plus aqueous, Cl minus aqueous, and we got the KSP expression then, which is going to be Ag plus and Cl minus. No coefficients, nothing like that. And what we're going to do is we're going to use our ice table here to figure out what we're going to plug in for these guys, right? We don't have any molar solubility. They haven't given us anything. So we should just have expressions to plug in here. Remember, these are 0. Change is plus x. 0 plus x, 0 plus x is just x and x. So again, we don't have any numbers anywhere to plug in, so we're just going to put those x's in here, and then we're going to do KSP right here, which they gave us. All right, so let's go ahead and let's do that. Remember, we got at equilibrium, we got x and x for Ag plus and Cl minus. So our KSP is 1.8 times 10 to the negative 10 equals x times x. So that's going to be 1.8 times 10 to the negative 10th equals x squared. Square root both sides, and I should get a molar solubility of 1.3 times 10 to the negative 5th, and molar solubility is just molarity. All right, I know that's kind of a pain, right? Just know that when they say molar solubility, you solve for x unless they state it as like the molar solubility of Cl minus. If you want KSP, you got to find those equilibrium concentrations of KSP. Remember that the AgCl, or the salt I give you, never affects equilibrium. It's just the ions that I give you, okay? So that's it for today. There's practice. Please try out that practice. Try it out on your own. Remember to always write your KSP expression. Always do an ice table if you get stuck with these, okay? Let me know if you have any questions. Have yourselves a great day.